So today's lecture, so the first 3 days were dedicated to tools and theory for ICE or DRT and stuff like that. Today, the presentation is more focused on hardware and how we are doing ICE measurements. The slides, as you are going, there are zero equations today. I will not be talking about any mathematics. There are a lot of slides describing electrical equipment. But it's not, as you're going to see, it's not done in electrical engineering stuff. Everything is in block diagrams. The goal is to explain to all of you how we are doing ICE, how we are doing measurements, how we are, what kind of equipment we are using, and what is our way of thinking when we are doing this. So there are, the first slide is a fork in the road. So if you have dedicated equipment for doing ICE, like Biologic or Zanner or whatever you might be using, then none of what I'm going to talk today applies. I can just stop here because we are not using none of this equipment. We are using off-the-shelf power supply units, electronic loads, and everything. So we can actually be quite flexible and do ICE measurements with comparably cheap equipment. What we have here in Dijon, it's not our first implementation. We have, I'm going to show examples from experiment in Graz in Austria, in Grenoble, France, something that we are currently doing in Ljubljana. I'm going to give you a background how we do, because this experiment generates a lot of data, a lot. And I'm going to tell you how we cope with this huge amount of data. Then we are going to talk about how you can recreate it, or if we cooperate, how we are doing things. People here in Dijon already saw what was happening. So the first thing, on my first day, I was talking about this. This is our first equipment that we did. It is a power conditioning unit for a PEM fuel cell. The idea was we wanted to make in-field, or actually it was required from us to be able to do in-field ICE measurements, not using laboratory equipment. And this is where everything started. So the basic idea is the following. Here we have the PEM fuel cell system. The gray rectangle actually represents what the outside world thinks that it is a PEM fuel cell. In essence, the PEM fuel cell is just here inside, and everything around it are supporting units. Formally speaking, in order for a PEM fuel cell to operate autonomously, only this part is needed. So the PEM fuel cell produces DC voltage depending on the stack size or whatever. And if somebody wants to connect it from the outside, it has to either change this DC to AC 220 volts and use it with a standard plug, or do a DC-DC converter so that it can adjust the required voltage for usage. And that was our goal. We developed a dedicated DC-DC unit that was capable to do the following thing. Outside world was looking at a constant voltage. I think it was 48 volts DC as a power supply, as a normal battery for a car, although it was a fuel cell. Inside, we were able to do excitation and measure it and perform ICE without this being noticed on the outside world. That was the basic idea. So the fuel cell was operating, and every X hours or X days, whatever was decided, we were able to excite the fuel cell within this internal loop, make a data acquisition with the voltage monitor that I'm going to talk about, and calculate ICE and do any further analysis that was then conveyed to some supervision unit or a real-time optimization unit or mitigation strategies or whatever. The user that was using the fuel cell outside was looking at flat 48 volts. So this is the first beginning where we realized that we are capable of doing these things without the need of dedicated equipment. And it turned out that doing this, it's quite easy. So if we have this random signal that we were doing, because it's just two switch going up and down. So let's go in details how it was done and how are we doing ICE now. So the idea was this was a 90 cell step. So we had to measure 90 voltages, 90 voltages plus one current. So altogether there was 91 signals that had to be acquired simultaneously and analyzed. So at each measurement cycle, we were generating 90 ICE curves for further analysis. So first thing was to generate an instrument, a plate, that was capable of measuring 90 voltages in parallel. So this is the part here. I'm going to explain how it works. It is non-electrical. This is not an electrical circuit, but a block diagram. So because it's so many channels, it is possible, but not with the price range that was required. So what we were doing is we were actually measuring really fast, jumping from first to the last channel like a multiplexer. Like think of it as if we have voltages here, and then we have one instrument, then we go with it, measure this, then switch, measure this, measure this, measure this, and then go around and do it one more time. So it does this constantly, like measure stuff. Because there are 90 voltages, doing these cycles with 90, it's really slow. We divided the banks into banks of 30. So now we have this like a Lego brick. We can measure voltages in groups of 30 top of the arm. Then there were some analog conditioning of the units, and all of it is going to a microcontroller that does ICE analysis. So this is the structure that we are having, and we are using it whenever we have an industrial grade system that has to be fitted with power and with ICE analysis tool. For laboratory exercises, we usually don't do this because because of the limited band frequency. This can go maximum up to 2 kilohertz of ICE. Otherwise, it produces quite a lot of data, and it is not capable of doing much more. But it turned out that for industrial applications, this is quite okay. So this is the actual implementation. You can see the 90 pins connecting to this. This down here is the stack, the PEM fuel cell stack. This is the side view, and here is the top view. This is the PCB that was generated. So because it was done for an automotive application, all the communication is based on CAN protocol that is quite common in the automotive field. So this is the baseline, the basis for what we have. And today, I don't think that I'm going to use all of the 3 hours that are allocated because there is not so much material. Let's see how it will go. I'm going to talk about the electrical components that are used here. I'm not going to talk about hardware implementation outside of the laboratory. I'm going to talk what kind of power supplies we are using and why are we using them, which data acquisition, and how we measure and analyze signals. So there are quite a lot of architectures that I'm going to describe. Reversible operation. And I'm going to go into details. Reversible operation, simple fuel cell, high power fuel cell, high power SO, FC, and so on. So as you can see, what I want you to take out from this picture is that we, in cases where we need, where we operate with high power equipment, what we are proposing is to use multiple electronic loads, share the power, actually use it as a Lego bricks. It is, none of this is our equipment. We are buying all of this off the shelf. I'm going to give you some guidelines, what you should look at and how we are generating these architectures. So first things first, fuel cell mode. So in a fuel cell mode, the fuel cell here is the main power source. And in this combination, because this acts as a power source, all that we need in order to characterize it is to change the current that we are drawing at. And we are doing this by using electronic loads, one or multiple of them connected in parallel. So if I try to draw an electrical circuit, it would be like this. I will draw a fuel cell as a battery, so just to get an idea. And the electronic load is as if a resistor that can be changed programmatically. So by changing this resistance back and forth, we are actually changing the current that is drawn from the fuel cell. And because we are changing the current, the fuel cell responds with changes of the voltages. Then we measure the current, we measure the voltages, and we can calculate it. There is a situation, particularly towards the ends of the IV curve, where and particularly in a short stacks, where the voltage drops quite low, in some cases even below 3 volts for a very, very short stacks. And then those cases, electronic loads do not operate properly. So in those cases, we need to add an additional power supply. I'm going to explain why in the details now. So if the fuel cell, so we have a version 1 where we have only an electronic load. If the fuel cell is not powerful enough, so the overall power of the fuel cell somewhere low, I would say like 500 watts or similar, then you can do all this analysis with a single electronic load. What we are using is we are buying electronic loads approximately with 350 watts, which means that if you have a more powerful system, you have to stack multiple electronic loads in parallel. So if I draw this again in an electrical circuit, the fuel cell, I will draw it again as a battery, and then we will have electronic load 1, and in parallel, electronic load 2. So what we usually do, we use the first electronic load to set the DC value. So we go at a certain IV point, and we use this one to do excitation. So how are we using it? We are buying electronic loads that have internal memory, like the excitation unit that we have here. So we are able to upload prior to the experiment. We're able to upload the excitation profile to the load, and when it's needed, we can just trigger it, and the electronic load starts drawing current according to a certain profile. So we can program sine waves, the things that I was showing in the last 2 days, this random binary signal. Practically, because it has a memory, you can do whatever you want. You have to be quite careful when buying this stuff. What is the frequency bandwidth of the electronic load? Some of them are really low, below 300 Hertz. You can easily find electronic loads that go sufficiently high for price tag around $1,000 US, which means that you can do this quite cheaply, and you are building a modular storage. The next case scenario is when we have a low power fuel cell. And what is happening is, I'm going to draw one more time. The fuel cell is a battery, and we usually put an electronic load here, as I said. Then I'm going to do like this, and so. So in order for electronic loads to operate properly, there is a minimum voltage that is a threshold. Below it, it will just shut down, because we are buying quite cheap electronic loads. If you buy high-end ones, this is not a problem. But we are buying cheap because we don't need anything special. So in order to increase the voltage here, we just make an additional power supply in this case, so that the voltage here is boosted. We always operated the power supply in constant voltage mode. Constant voltage mode. So they just follow the current that is required in the circuit. This was done here also in Dijon. We are putting the power supply in constant voltage, because in those regimes, almost all power supply have sufficiently high frequency bandwidth so they can follow the excitation unit, and it does not influence the ice curve. But we have to be careful how we measure the ice. Let me make one extra slide, because this is quite an important thing now. Okay, so there are options. You have to be really careful how you do the circuit architecture. So if we have like this is the fuel cell. Again, I'm drawing it as a battery just to pop out. And then we have, let's say, a power supply here. This is one option. And we can do excitation like here. And usually we measure voltage at these points. And current, I'm going to come back to the current. We measure it somewhere here. But by doing so, what we are actually looking at, we are not looking, if we say that this resistor is linear, what we are actually measuring, we are measuring ice on this complete set. So we are measuring the ice of a system that has a fuel cell and in parallel the power source. So we are going to combine these two ices. There is no other way how to measure it. And the output will not contain only the ice of the fuel cell, but there will be also influence of the power cell. That is why we always do a combination like this. So there is a power supply here. There is the electronic load here, fuel cell. Current is measured here. The current is the same, doesn't matter. And we measure the voltage at this point. And that is the way, because this is now all these two in parallel on one side and parallel second side. There will be influence of this undoubtedly. And that is why whenever we try to look for a power supply, that is why I was asking you what kind of power supplies you have in Dijon, is because of its bandwidth. So let me draw this so that you can get a better idea. Let us assume that the frequency, I'm going to do like frequency and modulus of the amplitude, of the impedance. That is more or less the most important thing. Let's say that the frequency region of the fuel cell is like this somewhere. And we are interested up to, let's say, as we are here at 50 kilohertz, right? So we have to find a power supply, and we have to find an electronic load that has a frequency band much higher than this. Why? Because then if we superimpose it, they will have flat line as wide as possible, and they will have this part somewhere in very high frequencies. The most important part is this slope here should be as far as possible from the slope of our fuel cell. Because if it's vice versa, let us assume that we bought a wrong power supply, and the power supply has a frequency characteristics like this. When we are going to start exciting our fuel cell, this part here, we will see the response of the fuel cell, but from this point onward, we're going to see the response of the power supply and not of the fuel cell itself. That is why we always operate the power supply in constant voltage mode, because if you look at the data sheet, the constant voltage mode has bandwidth most probably up to 100 kilohertz. And if you see on the exact same power supply, the constant current bandwidth, it can drop down even below 300 hertz. So that is why we always take great care of these bandwidths, because there is no way, although we are measuring voltage here, it is impossible, physically impossible, to detach the influence of the other part of the circuit. The other part of the circuit is present. Only thing what we can design is to make the other part of the circuit so with so high frequency band so that it doesn't influence the frequency response of the fuel cell. This is the only thing that what you have to take care of. When you buy a unit that makes excitation, let's say a biologic or Tanner or whatever you are using, and you are buying this box, everything, all of this together, the supplier already took care of this. And when you buy this instrument, the supplier will tell you, you can measure impedances up to 100 kilohertz. This means that their power supply for sure goes really high. It is detached from the fuel cell, so what you're going to measure is only the response of the fuel cell. Actually, you will always measure the response of the power supply too, but because its frequency range is so high, you will not see its influence. That's the most important part. So, that being said, by choosing a proper power supply, and this is not difficult, almost everything that you can get on the market is this sufficiently nice, and the price tags are really low. So I'm talking the power supplies that we're using is one German brand. Doesn't matter what you are using here in Daejeon, is one Japanese brand. Everything is well known, they're well established, and they have frequency bands in the area of 100 kilohertz. This means that this is quite okay. And I'll come back to the units that we are using. Okay, in electrolysis mode, and now the fuel cell is not a power supply, but the fuel cell is actually a load. We have to supply power to the fuel cell, to the electrolyzer. And we have a more complex scenario where we have to make a circuit that is capable of measuring ice both in electrolysis mode and fuel cell. And I'm going to discuss now these both scenarios. So electrolysis mode, this is a typical architecture that we are using. And this is the thing that we actually installed here in Dash. In this case, the stack is power consumer in the circuit. It's not as power source. So I'm going to put it as a load. So on this side, we have to somehow provide power. If we do not have any need for doing ice analysis, we can do really simple. I'm going to draw it now, the fuel cell, the electrolyzer as a resistor. I'm going to put EC unit, and all we need here is a power source with a proper polarity, doesn't matter, some voltage. It will deliver some current, and hydrogen will start popping up on this side. So this is the simplest scenario. We can operate it, and that's it. But if we would like to make ice, there are two options how we can do it. Either we somehow start changing the voltage here, or we somehow start to change the current that flows here. So we have to decide which signal are we going to use for excitation. In our case, what we are doing with this architecture here is we have this excitation unit that I'm going to go into details. And this excitation unit runs in a form of current source. So let me draw an electrical figure, a little bit more detailed, so that I can scribble a little bit more. So we have on this side our electrolyzer. I draw it as a resistor, as a load. So this is the EC unit. And this is a current source. This is our excitation unit. And then there is a main power supply that is installed already here. So our excitation, so this power supply, we put it in constant voltage mode. It just follows, and because in constant voltage mode it has high bandwidth, it will not influence the impedance of the electrolyte. In this unit here, we have pre-programmed excitation signals. And on demand, and I'm going to show you details how it's done, on demand, this excitation unit will start superimposing current here. And because this current will now flow through every part of the circuit, it will go through the electrolyzer. The electrolyzer will change its voltage accordingly. It will react. These fluctuations of the voltages will reverberate throughout the circuit. This part here keeps constant voltage. It will not change, but the current will pass through it. And because it is in constant voltage mode, it has high frequency bandwidth, it is capable of reacting without changing the current. And these voltage changes will affect only our excitation unit. And our excitation unit is designed in such a way that it has a bandwidth of more than 100 kilohertz. So it is capable of reacting. So all the reactions that are generated by the electrolyzer unit will not be distorted anywhere in the circuit. This means that if we then measure current here and voltage on the excitation unit, the signals that we are getting are only the influence of the electrolysis unit, which means that when we calculate V over I in that fancy way, the impedance is only from the EC unit. And that is what we wanted. Because if we made a different approach, if we put this in a constant current mode, which means that this would be like this, it will distort all the frequencies that are higher. I'm now popping up some number. I can't remember what was the power supply that was here. It would have destroyed all the frequencies above 300 hertz, which means that it wouldn't. Sorry, I clicked Siri. Mistake. So this is the electronic circuit that we have here in Darshan. This is how we do electrolysis. There is one peculiar stuff about our excitation unit. It is power limited. It cannot provide more than 500 watts. It means that, sorry. It means that our unit at this moment can provide from 0, or to be more precise, from 6 up to 120 amps. And its voltage, accordingly, here the low voltage doesn't matter. The high one is 500 divided by 120. It's the maximum voltage that it can occur. So because we are going to run it up until 100 amps at Darshan, it means that our unit, the voltage should not ever exceed 5 volts. But the stack that we have here will, in OCV, it has 17 volts. So what we have to do in order to operate it, we have to make sure that our excitation unit stays within these limits. How are we doing it? We are doing it with using your external power supply. So as we increase the current, because we are controlling everything through current here now, not through voltage, as we increase the current, we are moving your EC unit like this. It's IV curve. We are moving the set point of the EC unit higher and higher on this IV curve. It means that its voltage, let's use the proper colors, its voltage will increase. Since this is in constant voltage mode, the voltage of the power supply stays constant, which means that the change of the electrolyzer will be seen by our excitation unit. So at some point, our excitation unit will cross the threshold of 5 volts, and it will go into a safe mode operation. In order to prevent that, we have to bump up the main power supply to another voltage level, and this will cause immediately the voltage of our power supply to drop. This effect, this juggling up and down of voltages, is not seen by the electrolyzer unit because of the high bandwidth of the power supply and of the excitation unit. They react so quickly that they balance out the circuit before the electrolysis unit even realizing that they've changed voltages. It was when I draw it like this, it seems rather bizarre and rather counterintuitive. I mean, if you had a basic course of electrical circuit theory, you'll say, yes, this looks logical on paper, but when you see it in real life, so this is how we're doing, and this is what we were actually programming the last 2 days. Actually, not me. Guys here at Darshan Lab were capable of doing that. So now we have an architecture that I explained here that operates under these conditions and is capable of controlling the EC unit that it has here. So what I wanted to say is, in the overall power consumed by the fuel cell, by the electrolyzer, this much of that power is provided by the power supply unit, and only maximum 500 watts is provided by the excitation unit. So if you want to go higher, you can. You just have to buy more powerful external power supply. Our excitation unit just adds up maximum of 500 watts. This means that even in high power industrial installations, we can install this unit quite safe. Okay. Next, reversible mode. So this is something what we are actively doing in Graz University. There is a reversible solid oxide stack, and there are two circuits in parallel. So let's draw this in a more electrical schematic way. So we have the stack here. I don't know how to draw it because at one point it will be load and another point it will be source. So I will say that on this side I will draw the EC mode, and on this side I'm going to draw the FC mode. And there is a switch, a high power relay that can go here, and we are here in electrolysis mode and a fuel cell mode. And if it goes here, we have our excitation unit. Excitation unit, the power supply. And then we switch this and use the same circuits all the way. So, strictly speaking, this part here is what we have in Dijon. And what we have here is a simple fuel cell mode. And we are capable of doing this. Actually, we are doing this constantly for some time now. The going from FC to EC mode happens every 48 hours. It's done automatically, so it goes up, down, IV curve, ice, operates some time, goes down, switches up, ice, and it's cycling. I don't know how long time, quite a lot, and it's doing it automatically all the time, and with the same equipment that you have it here. So when I was talking that we are using off-the-shelf instruments, this is what we have. So the excitation unit that you have it here is the only thing that is developed by us. For the power supplies, we use some German company iTech because it's near our borders. For electronic loads, we are using Chinese brand Rigol. I think that you might know it. It's a really, really cheap, low end. One might say that even I don't know if you want to be really, really critical that on some edges, on the edges of the operating conditions is not performing properly and stuff like that. But despite all of it, turns out that it operates quite okay. For really, really high power installations, we do have one water-cooled electronic load that can go up to 10 kilowatts. And we are using it just to level the DC where we operate. And then we use these small electronic loads to do excitation and measure ice curves. So these are the Lego bricks that we have when we do ice analysis. As you can see, we do not have a single dedicated ice equipment. Everything what we have is off-the-shelf instruments. So let's go into details about the excitation unit that we're using. It is a machine that on one side connects the external power supply that provides the main power in the circuit, and on the other side we connect the stack. This is how it looks inside, where you put the connectors with these wiring poles here. What it does actually is rather simple. It takes the current that comes from the main power supply, and this is a DC value, because the power supply is in constant voltage and there is nothing in the circuitry, and it provides a DC power. And this DC power then comes through a series of FET transistors. So FET transistors, you can look at them as mini switches up and down. And these switches start to add or draw a little current up and down on top of the current that is coming from the main power supply. And we can here generate whatever shape we would like. And because this superimposes What comes out then on the stack is the DC level of the main power supply plus the signal that our excitation unit is generating. And this is what comes out here. And it's actually the excitation signal that goes to the stack. Then going here, the circuit closes. There is one issue that is happening also here in Dijon. It happens with us all the time. Although you're operating in EC mode, it might happen that when you start up the circuit, there is one fault. There is a voltage here from the stack and voltage here of the power supply unit. And it might happen that this voltage is bigger than the one of the power supply. When you started, the power supply is 0 volts. This means that the polarity here will reverse and our electronics goes into safe mode. Safe mode because it says that the stack switch, we are expecting an electrolyzer, and now we are having fuel cells, so some current is coming through, although minimal. So you have to reboot it. There is a procedure how to do it. There is nothing will break, but the unit will go into safe mode. And this happens only during startup if you're not careful enough or something happens. Luckily enough, everything is safe. So as I already said, this hardware unit was developed through several EU projects, and everything is open source. When I say open source, this is the link to the complete documentation of everything that you need for this excitation unit. There are schematics, PCBs, explanation, characterization, everything is there. You can even produce it on your own. There are no fees, no licenses behind it, nothing. The key component is this power printed circuit board. Everything around it that you see here in Dijon in this box are all the off-the-shelf supporting components, some capacitors, some power supplies, some fans, Raspberry Pi unit, nothing special. So this green PCB is this part here, and that is the core of the unit. Everything else is off the shelf. So there are several options depending on the power, on the highest current, water-cooled options if you go really high, and so on and so on. These are the characteristics of the basic unit. You can see here So if you can see here, it goes up to 150 amps, and it's dependent on the cooling. So you can, formally speaking, you can connect them in parallel like this. So each of them produces 150 amps. So the output will be approximately 300 amps. We have never tried this configuration, but if necessary, it can be tested and tried out. So currently with this equipment that we can ship around within this project, we can safely measure, we can safely generate currents to 150 amps. If we want to go 200 amps, then we will have to have water cooling to the device. So this complicates a little bit the installation, but this is possible. We can go up to 200 amps if needed. Okay. So this was generating the excitation. The next thing that we have is how we measure current. As we were discussing here before me shipping the unit, there were 3 options. So a shunt resistor, a Hall probe, and a flux gate sensor. So let's discuss each and every one of them, just to have an idea what is what and what are the pros and cons. So a shunt resistor is the simplest way how you can measure current. Let's draw a really simple circuit. So we have let's say an electrolysis unit, DC, and we have a power supply, plus minus power supply, and we would like to measure current. How we can measure it? We can pop a really small resistor unit here that we know how many ohms it is. Let's say 0.1 ohms, and then we measure the voltage here. And the current is so the voltage is 0.1 times the current that is flowing. We can easily, so the current is actually 10 times the measured voltage. Because it's linear, it's flat out, this is what we can do. So what we shipped here is a small box like this. It's not a resistor like you're used to see, like a tubular cylindrical stuff, because it has those kind of resistors have some inductivity in it. It is a PCB-like, a chip-like unit that has practically no inductivity and no capacitance. It has some, but it's really low, and you can feel this capacitance and inductivity up to very high frequencies, I think towards megahertz level, which means it will not affect the impedance of the measurement of our impedance. The only con part is that we are constantly losing 0.1 square times I watts of power. So we have some loss of power constantly. There is another thing that is, regardless how we measure current, where do we measure the current formally? I'm going to add an additional slide because it caused us quite a lot of trouble, this thing. Although we are electrical engineers by training, we underestimate the influence of cabling. So the complication that we have was the following. I'm going to draw a fuel cell as a battery again. And we had I'm not going to complicate with excitation units and stuff like that. We have, let's say, ICE-capable device here. And we positioned our resistor shunt quite close here because on a measuring stand, we had here data acquisition, we had external power supplies and everything. So physically, it was easier just to put cabling here to measure it. And these cables are quite thick, like the ones that you already have in your fuel cells. And it turns out that just a couple of meters, 1 to 2 meters of cabling, if we move this shunt here or here, adds up 2 to 3 degrees of phase difference. So in high frequencies, instead of ICE looking like this, they were looking like this. And we were unable to realize where it comes from. So what we did is we took we took an oscilloscope and we start moving the shunt through the cabling, and you can see the sine waves just shifting on really high frequencies. So that is why it is, and a normal electrical engineer would say, well, yes, but you never think of it that the influence is so high, because when you put the equations down, you will see that it should be like this, but by heart you don't feel it. So that is why we always try to measure current as close as possible to the fuel cell itself. So because this is a PEM fuel cell, the Hall probe, this was with Hall probe, is this blue thing here. Here you can see it. So it's actually on the very spot where it is connected to the fuel cell. as close as possible. In the context of solid oxide fuel cells, you cannot put it in the furnace. It's 800 plus degrees. So you put it as close as possible on the cold side. Yes, there will be some loss, some degrees error in the high frequency band, but that is the only thing what we can do. So we have to put this current measurement as close as possible, physically close as possible to the stack itself. Okay, so as I already said, the shunt, so that's why I draw it like this. So the circuit goes around a couple of meters, so the shunt must be as close as possible to stack. Luckily, although we have a shunt here, we are not going to use it. We're going to use a different measurement device. So the second case scenario is a Hall probe. Being all here either chemists, material scientists, electrical engineers, we all know what Hall effect is. It's induction of electromagnetic field through around a coil that conducts current. So the sensor is like this blue rectangular ring thing. You put the cable through it, and it can feel current. It has really high frequency. It doesn't influence the flow, and it doesn't draw much power. So for any industrial applications where power is important, we are using Hall probe sensors. So as you can see, this is exactly the one that we were using here, the blue sensor, and it's easy as is. In laboratory cases where the precision is quite important, we are using something that is called flux gate sensor. This is the one, sorry, I will move this somewhere else so that you can see it better. Yeah. So this is the actual version that we bought it here in Dijon. It is a company that is producing flux gate sensors for CERN in Switzerland for the particle accelerator. They're one of the best in the world, not the only one. If you write flux gate sensors, you will find really huge number of producers. They are maybe an order of a magnitude more expensive than Hall probe sensors. That is why we are using them only in laboratory settings. So what is the difference, and why am I talking about this? Because they can be used as an excitation device at the same time. If you don't know how it works, I will take just maybe 5 minutes to explain to you how these things are working. Again, as you can see, we have a hole through which we put our conductor, our wire, and around the wire here, there are two cores. It's like a toroidal core divided on half. And then we have two types of wires. One wire that is called the drive wire goes around this internal coil, and there is a so-called sense wire that goes around the sensor itself, and everything, all of this is inside. And now the beauty part is this: when we let's say a scenario when there is no current flowing through the sensor, the drive coil, the drive wire, has to be driven with a square-like signal like this. And this is on purposely not drawn properly square, just to emphasize this part up and down here, because I'm going to need it in the lower pictures. So it goes up and down, this signal, it goes up and down like this. And because we have two types of cores in this coil, it induces electromagnetic field on one side, in one direction on the right coil, and in the other direction in the other coil, and then the sense wire can sense this, and it's try to determine the difference between the electromagnetic field in this wire versus in this half and versus in the other half. And because there is no external field, there is no current flowing through the sensor, both signals are symmetrical and they cancel out. And the output of a sensor is zero. If a current now starts to flow through this hole, this current will inevitably enforce electromagnetic field around it, and it will make an imbalance on these two parts of the coil. And this imbalance would mean that one part will become shorter and one part will become larger or longer. And when they cancel out, there will be a residual signal that has a frequency twice as much as the frequency of the current flowing through. There is some electronics that polishes this out and gives us a proper 2-time frequency of the current flowing through. And these sensors have such huge bandwidth because this switching here is occurring with the megahertz frequencies. So it can sense really, really, really minute changes really, really fast. And because they're doing these differential changes, they're really, really noise resilient. And on top of that, there is one really peculiar thing that you can do. This is now, I think the patent was filed 10 days ago, or maybe a little longer. You can use this wire, this driving wire here, as an excitation unit. Why? Well, instead of putting a symmetrical signal up and down, you can put an asymmetrical one. And this will cause imbalance in the toroidal core anyway, and this will, in essence, induce some minute current on the wire itself. So the wire itself will conduct some DC value, and these small coils will induce on top of it some form of excitation signal. And then we can measure the voltage, and then we can do ice. Why is this important? Well, automotive industry comes now in place, and you go to automotive manufacturers for electric vehicles, and you tell them that you have a sensor that is capable of measuring signals up to 1,000 amps. It's okay. While in the same time, it allows you to measure ice anywhere from 0 to 1,000 amps. And everything packed in a single box. And this is the patent that is going out. I think it already went out. How you can do this thing. And this is the sensor that we are using here in Daejeon. We've tried everything, and that's why we said, okay, it might be a little bit expensive. I think, please correct me, I think that is around $1,000 the price of a sensor, or we may be there somewhere. Okay, smiles. So that amount of money for a sensor, but the benefits are this. This is the noise comparison between the blue sensor that is Hall probe and the orange one that is this flux gate for a DC current of 32.3 amps. And this is zoomed out. As you can see, we're going from this delta is 0.3 amps. So in almost 1% range, this one has negligible noise level. And with such a negligible noise level, we can measure current so precisely that in a laboratory setting, this is really, really handy. This sensor has better characteristics than the shunt that I brought here, and the shunt has, I think, 0.5% accuracy. This one is far, far better, but accordingly, the price has sufficiently more zeros than the shunt. And this is one of the design choices. If we were doing, if the goal here in Dijon was to make industrial-like measurements, then we would have for sure went with probe sensor, because it's, I think it's something like $20, 50 times cheaper. It's illogical to buy anything more. But anyway, now we have, what we have here is this top-notch sensor where we can do really, really, really precise things. Okay, now a couple of slides more about how we measure voltages. And this is a problem, particularly in a really, really long stacks. The measurement equipment that is commonly available has limits on the potential difference. So the one that we have here in Dijon says that the voltage level on the first channel and the voltage level on the second channel must not be more than 10 plus minus 10 volts apart. And we're saying, yeah, like, okay, the voltage of the stack is 17 volts, so this is okay, everything's fine. Yes, but when we start to degrade the stack, at one point this voltage will go above 20 volts, which means that we are going to burn out the data acquisition module that we have, because we are going to breach this plus minus 10 volts difference. So in order to be able to do this, we have to take several things into consideration. First thing is, we are not measuring absolute voltage. So there is a ground level here. We are not measuring this. We are not measuring this voltage versus this voltage here, but we are measuring in a differential mode. So we are measuring voltages between cells. And this difference actually gives us the actual voltage of a cell. The last cell is measured towards the ground, but all the other cells are measured relatively to each other. And this is called a differential way of measurement. We're measuring two potentials among each other and not towards the ground. But this special attention must be paid, because we can be here on 10 volts and we can be here to 10.5 volts. So we are actually interested in 500 millivolts signal, but we are somewhere high. So special attention must be taken. That is why, as you have it here in Dijon, it's called isolated data acquisition system. I'm going to talk about it. And one peculiarity in this scenario is that the shunt is connected to its own data acquisition, because we don't know where the shunt will be connected. If the shunt was connected above the plus, then the shunt will be always higher than the stack. If the shunt was connected to the minus part, then we could have connected it to the last data acquisition module. But luckily, because here you have enough resources and there was one spare data acquisition card, we decided to be on a safe side, just in case somebody makes a positioning wrong, to put the shunt on its own data acquisition card. So even if the shunt is mounted on the plus side of the potential, nothing will break, because the maximum difference here will never exceed 20 volts. because imagine if somebody connected these wires somewhere here. So among these two, this wire will be on plus, I don't know, 30 volts, and this wire here will be around 10, and there will be huge difference, and some of these data acquisitions would burn out immediately. That is why we have to take care of this. Next thing scenario, isolated data acquisitions. And this is what you have here. This is what you get when you buy Zanner or biologic equipment or whatever equipment you're using. Why is this important? Well, there are two things. We usually measure really small voltages on high potentials. High potentials, I'm not saying kilovolts at this moment, but we are going to measure a couple of millivolts on a stack that has 20 volts or plus. So there is a chance that there is a breach due to some fault in the data acquisition or whatever, that this huge potential can go through the data acquisition system all the way down to our PC and the equipment, everything down. So it would be as if somebody connects directly the fuel cell stack to some internal point in the PC, and everything will just blow out and even make a fire. And that is why there are so-called isolated DAQ devices that have an internal protection that prevent these things to happen. But as I said previously, this protection is not almighty. It only protects plus minus 10 volts. The equipment that we are using, and it's, I think, so just for a comparison, 8-channel data acquisition that we use for industrial grade applications where volts can go above 300. For 8-channel, we are paying something about $15,000. And they have a protection of 1 kilowatt. You don't need it here, and you don't have it. You have plus minus 10 volts. That is quite okay, but we have to take some precautions. How are we going to connect the cell in order never to exceed this plus minus 10 volts? And that is why I was talking so much about positioning of these filters up and down. And finally, how are we measuring voltage? And the actual issue that I was talking about when I was introducing Kramer-Kronig from our experiment, where we have problems on high frequency ranges, is whether our data acquisitions measures simultaneously or interlaced. So if you open a data sheet and somebody says it is simultaneous sampling or interlaced sampling, it might not pop in your head what this means. This is quite important for high frequencies. So we usually measure at least 2 signals, voltage and a current. In a case in Dijon, we measure, I think, please correct me, I don't know how, is it 20 cell stack?
Yeah,
20, yeah. Cases. So we actually, here we measure 20 voltages and 1 current. So they're all together 21 signals. This would mean that there are additional here 20 such lines plus a red current. And if we measure simultaneously, which means that our data acquisition system is capable of measuring on exactly the same point all these signals. And we know that when we measured current here, this was exactly the same point where we measured the voltage. And then we can do ice. There is no phase difference, nothing. That is what everyone would expect. But the equipment that you have is not always like that. What you have here is a professional equipment, quite an expensive equipment. And that's why you don't have to worry. If you start pushing the price down, this is not within your reach. the next thing is, why is this is not in your reach? Because you have here 21 ADC converter. Imagine as if you have 21 instruments that measure in parallel, and each of them costs some money. If you don't have that funds, and particularly if you do industrial application or if you do mass production, you would like to cut costs as much as possible. And in this case, there is the scenario that comes, and it's called interlaced measurement, which means first we measure the first channel, then the second channel, then the third, then the fourth, and so on and so on. So when we see, and if we have 21 measurements, like here, we measure the first signal at this time point and the last signal at this time point. And there is a phase difference because we were waiting for this. And someone will say, well, okay, this multiplexer goes really, really, really fast. Yes, that is true. But if we go and measure 1 kilohertz signal, this 1 kilohertz signal changes fast also. And this phase difference becomes bigger and bigger as we increase the frequencies. And that was the problem that we have in France. We were using interlaced data acquisition, and above 1 kilohertz, a phase error occurred that wasn't the consequence of the fuel cell, but a consequence of our measuring a loop. And because this is a non-linear transformation, the Kramer-Kronig test failed. That is how we actually move it backwards. We were a little bit stingy, and for an experiment, we bought cheap data acquisition, and we paid a price that now we have limited ice. But at least it's a good teaching material, if not anything else. So, final thing, I think, and then we can make a break. Yes, final thing is filtering. So let me put another white slide here. Then we will make a break. So what we have here in Dijon, and let's discuss why is this important. So here I'm going to draw it on another mirror. So this is our excitation unit. It's not important at the moment. Your power supply here and your stack. I'm drawing it as a battery because I would like to see it as a stack, although it is an electrolyzer. So we are measuring voltages on each of these cells. There are 20 of these, and we have this flux gate sensor here as a 21st channel. And these signals are coming through. And we have to sample them. But if we take frequency characteristics of these signals, the signals will be, there is some noise, there is some signal level that we are putting inside, but on top of this, Mother Nature provides us with noise. A noise that goes to formally to plus infinity. So when you sample a signal, what you're actually doing is you are measuring it. You're measuring it in discrete points, and there is this problem of overlap. So it's not to bother you with a Fourier transform. The easiest way to see it is with this graph here. So imagine that we sampled only these points. One would say that we have sampled this red sine wave. But the problem is that through exactly those points, the green sine wave goes, and also the blue sine wave goes. And now the question is, what did we measure? There is no way for you to know what we measured. And that is why there is a formal theorem. It's called Shannon-Nyquist sampling theorem, which says you have to sample with twice the frequency of the highest frequency that you would like to see. So in our case, we are going, and I'm going to explain now, we are going to up to 10 kilohertz. So we have to sample up to 20 kilohertz. And in such a way, we will be able to distinguish every frequency from 0 to 10 hertz without any error. Go open Wikipedia or wherever and ask for Shannon-Nyquist sampling theorem, and that is the case. So it's ×2. So how do we achieve this? In essence, we have our signal that goes like this slowly, but then we have infinitely long noise level. So what we have to do is, before we start measuring these red signals, we have to filter them. Filter and cut everything above 10 kilohertz. So let's say here, and then it's 0. There are no signals above 10 kilohertz. And then we put these filtered signals, 21 of them, to the data acquisition system that we set, and we sample here with 20 kilohertz. In such a way, we can now ensure that the things that we measured on the EC part will be recreatable when we come to the PC. And yesterday we realized that we made a mistake when designing these filters. Due to either miscommunication or misunderstanding on my side, we deliver filters here that go up to 10 kilohertz. It turned out that we would like to have impedances much higher than this. So we have to redesign this part. It's not mission critical. We can start the experiments now, but the ice curves will be limited to 10 kilohertz. Then it turned out that there is an additional limitation. The maximum data acquisition that we can do here is 200 kilohertz. 100 kilohertz, which means that the maximum frequency that we are going to see is 50 kilohertz. So what I have to do now is redesign the filters from 10 to 50 and just reconnect new filters, and everything would be corrected accordingly. But these small details are really important, because if you make a mistake at any of these points, the results that you're going to get will be corrupted. You will not see them as a jibber jabber, but Kramer Chronic will start to fail, and a lot of stuff will start to fail, and then you will have to go through all of these steps that I described, out at which step I made a wrong measurement. So that is why I said I'm going to stop now. Just one sentence, and that's it. So that is why I said at the very beginning on my presentation that if you're using a dedicated equipment for ice, all of this that I was talking today is already built in. So you take it, you plug it, play, and it works, because somebody took care that all these peculiarities are in place.